Welcome to Lecture 2. This week I'm going to start by talking more about linear systems, topics which ideally I should have done last week, but I didn't have time to fit it in. And then I want to talk about matrices more generally, and I want to finish by talking about the inverse of a matrix. First, let's talk again about linear systems. Variables which correspond to pivot columns are called basic variables, and the other variables are called free variables. So, for example, look at this linear system. I've written on the right as a system of three equations, and on the left I've written this in the form of an augmented matrix. And this augmented matrix is in reduced row echelon form. We can see where the pivots are. The pivots are in the first column and in the second column. So column 1 and column 2 are the pivot columns. That means that the first two variables, variable x1 and x2, are the basic variables, and the other variables, which in this example is just x3, are the free variables. We can write the general solution to this linear system like this. x1 is a function of other variables. x2 is a function of the other variables. That's how we write the basic variables. And for free variables, we just write that x3 is free. In other words, x3 is a free variable. What this means is that we could choose any number that we wanted for x3. After we've chosen some number for x3, we use the formulae to calculate x1 and x2. Free variables can be any number. The basic variables are then determined by the formulae. So, for example, if we chose x3 is equal to 0, then we would get the solution 1, 4, 0. x1 is 1, x2 is 4, and x3 is 0. Or we could choose a different number for x3. We might choose x3 is equal to 1, say. And then using the formulae, x1 must be 6, x2 must be 3, and x3 is 1. Find the general system of the linear system whose augmented matrix has been reduced to this form. This is in row echelon form. It's not in reduced row echelon form, it is in row echelon form. To be able to write down the solution, we need it in reduced row echelon form. So we're going to have to do some row reduction on this matrix. I'm going to do two elementary row operations at the same time. I'm going to do R3 plus R2, and that will be the new row 2. And I'm going to do 2 times row 3 plus row 1, and that will be the new row 1. That gives me some zeros just here. I also want 1 just here. I want every pivot to be 1, and above every pivot I want every entry to be 0. So I want 0 above the pivot. Multiply row 2 by half, that gives me my 1, and then the next step is to get rid of the 2 here. 2 multiplied by 2 times 1 will give 0. So we're going to do row 1 minus 2 times row 2. Or minus 2 row 2 plus row 1 will be the new row 1. Now we are in RREF, reduced row echelon form. This augmented matrix has 6 columns, but remember the right-hand column is always for the numbers on the right of the equal sign. So if we have 6 columns, that means we have 5 variables. And we can write down the system like this. x1 plus 6x2 plus 3x4 is 0, x3 minus 4x4 is equal to 5, x5 is equal to 7. Which variables are the basic variables and which variables are the free variables? Where are the pivots? We have a pivot in the first column, a pivot in the third column, and a pivot in the fifth column. So x1, x3, and x5 are basic variables. The other variables, that's x2 and x4 for this example, are free variables. Then we can write down the general solution to the linear system. We've said x2 and x4 are the free variables, so we can just write x2 is free and x4 is free. And then for the other variables, for the basic variables, we have formulae. For example, the top equation in the system above, x1 plus 6x2 plus 3x4 is equal to 0. Rearrange that, that's the same as x1 is minus 6x2 minus 3x4. Now, remember, a linear system is consistent. The definition was if it has at least one solution. This theorem says a linear system is consistent. A linear system has at least one solution if and only if the rightmost column of the augmented matrix is not a pivot column. So in other words, a linear system is consistent if and only if an echelon form for the augmented matrix does not have a row which looks like this. 0, 0, 0, 0, and then finally a number b which is not 0. If we have anything like this in our echelon form, then we know that the linear system is inconsistent. If a linear system is consistent, so if there's at least one solution, that means either there's one solution or infinitely many solutions, then the solution set contains either a unique solution, that happens when there's no free variables, or it contains infinitely many solutions. And case 2, infinitely many solutions, occurs when there's at least one free variable. There's a typo here, this word should be 1. Screenshot from your textbook. How do we use row reduction to solve a linear system? Step 1, write the augmented matrix of the system. Step 2, use the row reduction algorithm. That's Gaussian elimination or Gauss-Jordan elimination to obtain an equivalent, a row equivalent augmented matrix in echelon form. Decide whether the system is consistent. Look to see if the right-hand column is a pivot column. And if there's no solution, we stop. If the right-hand column is not a pivot column, then we can go on to step 3. If necessary, we continue our row reduction until we get a reduced row echelon form. Step 4, go back to the systems of equations, go from an augmented matrix to equations, and then write down the solution so that every basic variable is given by a formula, and we say that which variables are the free variables. So for example, how many solutions does the following linear system have? Either there's 0 solutions, or there's 1 solution, or there's infinitely many solutions. Step 1, we need an augmented matrix for this, and then we're going to reduce this to row echelon form to see if the linear system is consistent. Soon I'm going to stop showing you all of the steps. I'm just going to ask you to check it. But for now, I'm going to show you every step in a row reduction. First thing is, we don't want a 0 at the top of the first non-zero column. I want a number here which is not 0. So I can swap 2 rows. I could either swap row 1 with row 2, or I can swap row 1 with row 3. I'm choosing to swap row 1 with row 3. Underneath the pivot, I want zeros. So I want to get rid of the 3 at the start of the second row. So I'm just going to do minus row 1 plus row 2 will be the new row 2. For example, minus 7 minus minus 9 is minus 7 plus 9, or 2. 8 minus 12 is minus 4, and so on. What do we want next? Next, we want to move on to the next pivot. This 2 is a pivot. Underneath this 2, I want zeros. I want to change this number 3 to a 0. So I'm going to do minus 3 over 2 R2 plus R3, what becomes the new R3. This matrix is now in row echelon form. Where are the pivots? Here's the pivots. I've put them in green. The pivot columns are the first, second, and fifth columns. Because the sixth column is not a pivot column, that means the linear system is consistent. So we've ruled out the possibility of there being 0 solutions. Now we know that there's either one unique solution or there are infinitely many solutions. The basic variables are the variables which are corresponding to the pivot columns. So x1, x2, x5. Which variables are the free variables? The other variables. So it must be x3 and x4 are the free variables. Remember the last theorem? The last theorem said if you have any free variables, then that means there's infinitely many solutions. Because we have free variables, that means there's infinitely many solutions to this linear system. And I want to finish this section by talking about homogeneous linear systems. A system of linear equations, or a linear system, is said to be homogeneous if the constant terms are all 0. So in other words, we have something like this. If all of these numbers on the right-hand side of the equal signs are 0, then our linear system is called homogeneous. Now note, every homogeneous linear system is consistent because there's always at least one solution, because 0, 0, 0, 0, 0 is always a solution. If we replace every one of these x variables by 0, we get 0 plus 0 plus 0 plus 0 plus 0, which is 0. It always works with putting 0 in if we have a homogeneous linear system. This solution, the 0 solution, is called the trivial solution. If there are other solutions, then they're called non-trivial solutions. So just to summarize, a homogeneous linear system has a non-trivial solution if and only if it has at least one free variable. If there's no free variables, then we know there's one unique solution. If there are some free variables, or at least one free variable, then we know that there are infinitely many solutions. For example, use Gauss-Jordan elimination to solve this homogeneous linear solution. We need an augmented matrix, and then we're going to reduce this augmented matrix. But now I'm going to leave this for you to do. This augmented matrix can be row reduced to this one. But I'm leaving that for you to check. Often in these lectures, I'm going to ask you to check things, and do please try to check some of them, because it's very easy for me to make typos when I'm typing these slides out. Let me know on the discussion boards if you find a mistake in my calculations. For now, let's just assume that this is correct. After we've got our reduced row echelon form, we go back to systems of equations. We write down the corresponding linear system, and then after we've got that, we can write down the solution. x2, x4, and x5 are the free variables. x1, x3, and x6 are the basic variables. Because we have free variables, we know that we have infinitely many solutions. I'm going to finish with a couple of theorems. The first theorem says if a homogeneous linear system has n variables, and if the reduced row echelon form of its augmented matrix has r non-zero rows, then the system has n minus r free variables. From this, straight away, we can say a homogeneous linear system which has more variables than equations must have infinitely many solutions. If there's more variables than equations, then we must have at least one free variable, so therefore we must have infinitely many solutions. Now I want to change topic. I want to start talking about matrices in more general. We've been using these rectangular arrays of numbers, and we've been calling them augmented matrices so far. And we've been using them to abbreviate linear systems. But now I want to discuss what a matrix is and what we can do with them. Formally, a matrix is just a rectangular array of numbers. The numbers in a matrix are called the entries. And before I go on, let me just point out the plural of matrix is matrices. You're not going to lose any points in an exam if you write matrices, but the correct English is matrices. These are matrices. The size of a matrix is number of rows by number of columns. So, for example, look at the first matrix in the example. That matrix has 3 rows and 2 columns, so that's a 3 by 2 matrix. The next matrix has 1 row and 4 columns. That's a 1 by 4 matrix. Then I have a 3 by 3 matrix, a 2 by 1 matrix, and then finally I have a 1 by 1 matrix. A matrix with only 1 row is called a row vector. A matrix with only 1 column is called a column vector. Typically, we're going to use capital letters, capital A, capital B, capital C, etc., to denote matrices, and we're going to be using lowercase letters, small a, small b, small c, etc., to denote numbers. The entry, which occurs or exists in row I and column J of a matrix capital A, will be noted by small a subscript ij. So for example, if I have a general 3 by 4 matrix, that's 3 rows and 4 columns, I could write it like this. A11, A12, A13, etc. The entry in row 2, column 4, is called A24. It's not A24, it's A24. And if we, in general, if we had an M by N matrix, that's M rows and N columns, we could write it like this. This is row 1 of the matrix. Looking along this row, the first of the 2 indices is always 1. It's A11, A12, 13, A14, etc. It's always 1 first because we're in row 1. Row 2, A21, A22, A23, etc. Somewhere in the middle, row I, and then row M. Entries in the first column, in column 1, always have second index 1. A11, A21, A31, A41, etc. Always the second number is 1. Column 2, column J, and then finally column N. The entry which is in row I and in column J is Aij. Now, sometimes we might want to have a shorter way of writing this. Instead of writing the whole thing at the top of the slide, I might just want to write A is equal to square bracket Aij, close square bracket, subscript M by N. Or if I'm being extra lazy, and if I don't specifically want to say how big the matrix is, I could just write this as capital A is equal to square bracket Aij, close square bracket. There's another way to know an entries. The entry in row I and column J of a matrix capital A, which I've been calling small a ij, it could also be written as round bracket capital A round bracket subscript ij. So for example, if A is the 2 by 2 matrix 2 minus 3, 7, 0, then the entry round bracket capital A round bracket 1, 1 is equal to 2. Entry 1, 2 is equal to minus 3. Entry 2, 1 is equal to 7. And entry 2, 2 is equal to 0. For vectors, and what I mean is 1 by n and m by 1 matrices, it's common practice that instead of using capital letters, we use bold lowercase letters. So for example, bold A, or if you're using a pen, we could write underlined A, is a row vector or a 1 by n matrix, and bold B or underlined B, if I'm using a pen, is this column vector or n by 1 matrix. A matrix which has the same number of rows and columns is called a square matrix. If it has n rows and it has n columns, then it's a square matrix of order n. On a square matrix, we can talk about the main diagonal. The entries A11, A22, A33, A44, all the way up to ANN. As the ones on the diagonal from the top left to the bottom right are called the entries on the main diagonal of this square matrix. Let's talk about some operations on matrices. First of all, two matrices are equal if two rules are satisfied. First of all, they must have the same size, and the corresponding entries must be equal. For example, small aij must be equal to small bij for all I and all j. If capital A and capital B have the same size, then we can add them together, or we can subtract one from the other in the obvious way. So for example, let's suppose I have three matrices, capital A, capital B, and capital C. I could add A and B together just by adding the entries in the same position. So for example, top left, that's row 1, column 1, or entry 1, 1. I can do 2 plus minus 4 to give me minus 2. And then I could do 1 plus 3 gives me 4. And so on. Just add the entries in the same position together. Or same thing for subtraction. 3 minus 1 is 2. And so on. Now, we can only do this if the matrices are the same size. A plus C, we can't do. The sizes are different. B plus C, we can't do. We can't do A minus C, and we can't do B minus C. Something else we can do is we can multiply a matrix by a number. And again, we do this in the obvious way. Again, I've got three matrices, A, B, and C. If A is the matrix 2, 3, 4, 1, 3, 1, then 2 multiplied by A, just multiply every entry by 2. 4, 6, 8, 2, 6, 2. Or I could do minus B, by which I mean minus 1 multiplied by B. Multiply every entry in B by minus 1. Or I could do 1/3 C. Multiply every entry in C by 1/3. If we have a matrix where all of the entries are 0, then it's called a zero matrix. And there's two ways to write this, depending on if we care about the size of the matrix or not. If we care about the size of the matrix, then we call this 0 subscript m by n. If we don't care about the size, or if we're just being lazy, we can just call this 0. For example, here's some 0 matrices. A 2 by 2 0 matrix, a 3 by 3 zero matrix, a 2 by 4, 2 rows and 4 columns, 2 by 4 zero matrix, and so on. Very, very quickly, let me talk about some of the rules of adding, subtracting, or multiplying matrices by constants. If we have 3 matrices of the same size, and if we have 2 numbers, then A plus B is equal to B plus A, because we're just adding the entries together. And we know if we're adding numbers together, it doesn't matter which order we add them together in. So the same for matrices. A plus B plus C is the same as A plus B plus C. Same reason. A plus the zero matrix is just A, because for each entry we're just adding on 0, so it stays the same. And of course A minus 0 must be A. A number R multiplied by A plus B is the same as RA plus RB. R plus S multiplied by A, RA plus SA, and R multiplied by SA is the same as RSA. These should all be clear to you. This is just the same rules that we have for numbers. If I have R matrices, A1, A2 up to AR, and if these are all of the same size, and if I have R numbers, C1, C2 up to CR, then we can write down C1A1 plus C2A2 plus C3A3 plus C4A4 plus dot dot plus CRAR. This is called a linear combination of our matrices. And when we do this, the numbers are called the coefficients. We'll talk about linear combinations later. We'll talk about linear combinations quite a lot in this course. Next thing I want to talk about is matrix multiplication. I want to multiply 2 matrices together. And we don't do this in the obvious way. When matrices were first invented, when people were first trying them out, they thought we could multiply 2 matrices together just by multiplying the entries together, just like we do with addition. But it turns out that that's not worth anything. It's not, doesn't have anything useful to tell us. We have a different way to consider matrix multiplication, which does tell us things, which is useful in mathematics. If I want to multiply A with B, I need the sizes to satisfy particular rules. I need to multiply an M by R matrix with an R by N matrix. And then after I've done that, the product AB is going to be an M by N matrix. And the rule is that to find the entry in the ith row in the jth column of AB, we need to take the ith row of A and the jth column of B, and then we're going to multiply each entry from row I of A with the corresponding entry of row J of B, and then we're going to sum them, we're going to add them together. That's a bit wordy. I think it'll be easier to understand if we do an example. Multiply the following 2 matrices together. A is a 2 by 3 matrix, 1, 2, 4, 2, 6, 0, and B is a 3 by 4 matrix, 4, 1, 4, 3, 0, minus 1, 3, 1, 2, 7, 5, 2. Because we got a 2 by 3 matrix and a 3 by 4 matrix, these numbers are the same, 3 and 3. The product is going to be the other numbers. The product is going to be a 2 by 4 matrix. Product is going to be 2 by 4. Okay, so the product is going to look like this. Each one of these squares needs to have a number in it. We have 8 squares, so we need to do 8 calculations. For example, let's suppose I want to do this one. Let's say I want to calculate the entry in the second row and the third column. The rule is I need the second row of the first matrix, and I need the third column of the second matrix. And then what we do is we multiply the first two numbers together. The first numbers are 2 and 4. Multiply them together to get 8. The second numbers are 6 and 3. Multiply them together, we get 18. And the third numbers are 0 and 5. Multiply them together to get 0. And then we add these together. 8 plus 18 plus 0 is equal to 26. And that goes just here. Let's do another one. Let's suppose I want to find the entry in row 1 and column 4 of AB. Then I need row 1 of the first matrix and column 4 of the second matrix. And I do the same thing. The first numbers, 1 and 3, multiply them together. The second numbers are 2 and 1, multiply them together. And the third numbers, 4 and 2, we multiply them together. A bit like doing the dot product between two vectors. 1 multiplied by 3 plus 2 multiplied by 1 plus 4 multiplied by 2. And that's 13. So we write 13 in row 1, column 4 of AB. I'm going to leave the other 6 entries for you to check. When you have a free moment later today, load up this slide, slide 39, and calculate them yourself, and just check that I haven't made a mistake here. Now, let me remind you, we can only multiply two matrices together if the sizes are right. And in particular, we can only multiply two matrices together if the inside size numbers are the same. M by R and N by, so an R by N. These in numbers, these R's need to be the same. And if that's true, then the outside numbers are going to give us the size of the product. AB is going to be an M by N matrix. So, for example, an example I've taken from a textbook, if A is a 3 by 5 matrix, 3 rows and 5 columns, and if B is a 5 by 2 matrix, what are the sizes of AB and BA if they are defined? First, let's look at AB. A is 3 by 5, B is 5 by 2. These inside numbers are 5, and these are the same. So this is defined, and to define the size of AB, we look at the outside numbers, 3 by 2. We cannot calculate BA because the number of columns of B is not the same as the number of columns of A. Now a question for you. Suppose that A, B, and C have matrices of the following sizes. Which of the following is correct? One of these is correct and the other 3 are incorrect. 2 people chose number 1, 3 people chose number 2, and 4 people chose number 3. I can tell you that the correct answer is number 3. First of all, look at AB. If we're looking at AB, the inside numbers are the same. It's 4 and 4, and then the outside numbers give us the size, 3 and 7. For BA, imagine swapping the positions of these two, so B is on the left and A is on the right. Then the inside numbers are going to be 7 and 3. These are not the same, so BA is undefined. Let's do another one. Which of these are correct? Which of these is correct? 1 is correct and 3 are wrong. This time, 10 people chose number 1. And that is the correct answer. Let's do one more. Yes, number 1 again. Now, one more slide before I take a break. In general, if we have an M by R matrix and an R by N matrix, then to calculate the entry in row I and column J, we need row I of capital A, and we need column J of matrix B. And then the formula is, we multiply the first two together, so it's AI1, B1J, and then we do plus AI2, B2J, and so on. This formula in this blue box is called the row-column rule for matrix multiplication. And now I'm ready to take a 10-minute break. We're going to continue the lecture at 3 o'clock. Space in the term for 13 classes, but because something always comes up, we always lose a lesson. Usually we lose a lesson. I'm planning 12 lessons, and then we can make changes later if necessary.
Hocam, can I ask?
And now let's continue. The identity matrix is a square matrix has ones on the main diagonal and zeros everywhere else. If we're interested in the size of the matrix, we can write this as I subscript n for an n by n square matrix. If we don't care about the size, or if we're just being a little bit lazy, we can just write capital I. So for example, I2, or just I if we're being lazy, is the 2 by 2 matrix where the main diagonal is 1 and the other numbers are 0. Or I3 is the 3 by 3 identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. Number 1's on the main diagonal and 0's everywhere else. Now note, if A is a 3 by 2 matrix, sorry, that's a typo, that should be a 2 by 3 matrix. A is a 2 by 3 matrix. Then we can do A multiplied by I3, because 2 by 3 multiplied by 3 by 3, the inner sizes are the same. And we're going to end up with a 2 by 3 matrix. And if we calculate this, if we do, say, first row by first column, A11 multiplied by 1 plus A12 multiplied by 0 plus A13 multiplied by 0, that just gives us a 1, 1. If we do the same thing for every entry, we find that we just get A. Or if we multiply on the left by I2, it needs to be I2 so that the sizes match up. A 2 by 2 matrix multiplied by a 2 by 3 matrix, so the inner sizes are 2 and 2, we end up with a 2 by 3 matrix. And again, if we do this, for example, let's suppose we do row 2, column 3, to give us row 2, column 3. It's going to be 0 multiplied by A13 plus 1 multiplied by A23. That's just A23. We get capital A again. Let's go through some properties of matrix multiplication. If we've got 3 matrices and we multiply them together, it doesn't matter which order we do them. It doesn't matter where we put the brackets in. A multiplied by BC is the same as AB multiplied by C. A multiplied by B plus C is the same as B plus AC. B plus C multiplied by A is the same as BA plus CA. A number R multiplied by AB is the same as RA multiplied by B, or A multiplied by RB. If we have a number, it doesn't matter where we put the number. And I multiplied by A is always equal to A, and A multiplied by I is always equal to A. For example, let's suppose we have A is 513 minus 2 and B is 2043. Calculate AB and BA. Now, I'm going to leave this for you to check. Check there's no typos on this slide for me. Check that AB is 14.3 minus 2 minus 6. And also check that BA is 10.2 29 minus 2. So note that AB is not the same as BA. Now this is different from numbers. In numbers, we know that AB is equal to BA. But for matrices, this is not true. In general, so usually, most of the time, AB is not the same as BA if capital A and capital B are matrices. There's 2 more rules which don't carry over from numbers. In numbers, if we know that AB is equal to AC, then there's 2 possibilities. Either A is the number 0 or B is equal to C. But that doesn't carry over to matrices. Capital AB equal to capital AC does not imply A is the 0 matrix or B is equal to C. And the third rule, which doesn't carry over from numbers, is in numbers, we know that if AB is equal to 0, then either A is 0 or B is 0. But that's not true in matrices. capital A, capital B equal to 0, equal to the 0 matrix, does not imply that capital A is the 0 matrix or capital B is the 0 matrix. And I'm going to show that to you with two examples now. For example, let's A be the 2 by 2 matrix 0, 1, 0, 2, B is a 2 by 2 matrix 1, 1, 3, 4, and C is a 2 by 2 matrix 2, 5, 3, 4. Now, clearly here, B is not the same as C, and A is not the 0 vector. It's the 0 matrix. But I'm going to leave it to you to check that AB is 3, 4, 6, 8, and AC is also 3, 4, 6, 8. And I'm also going to leave it for you to check that if we multiply 0, 1, 0, 2 by 3, 7, 0, 0, we get the 0 matrix. But neither matrix on the left is the 0 matrix. So most of the rules from numbers carry over, but these three rules in particular do not carry over. Transpose of a matrix. If capital A is an m by n matrix, then the transpose of A, which we write as A superscript capital T, is going to be an n by m matrix. We go from m rows and n columns to n rows and m columns. And we get this by interchanging the rows and columns of A. So in other words, that means the first column of A transpose is the same as the first row of A. The second column of A transpose is the same as the second row of A, and so on. Think of a transpose like this. Let's suppose we write our matrix on a piece of paper, and then we're going to turn the piece of paper over. And we're going to turn it over in such a way that the top left stays the top left, and the bottom right stays the bottom right. So imagine you're holding your bit of paper at the top left and the bottom right, and then you flip your paper over. That's what transpose means. So for example, if capital A is the 3 by 2 matrix, 2, 3, 1, 4, 5, 6, then A transpose is the 2 by 3 matrix, 2, 1, 5, 3, 4, 6. The first row of A becomes the first column of A transpose, and so on. If capital C is the 1 by 3 matrix, or the row vector 1, 3, 5, then C transpose is the 3 by 1 matrix, or the column vector 1, 3, 5. And if we just have a 1 by 1 matrix, we take the transpose, nothing happens. Now note that because row I of A has the same entries as column I of A transpose, and column J of A has the same entries as row J of A transpose, we have a formula. The ijth entry of A transpose is the same as the jith entry of A. Just because we're swapping rows with columns and columns with rows. We have another T word, trace of a matrix. If capital A is a square matrix, it has to be a square matrix, then the trace of A, and we write this as small t, small r of A. This is defined to be the sum of the entries on the main diagonal of A. Trace of A is only defined if we have a square matrix. We don't have a trace of a matrix which is not square. So, for example, there's two matrices here, A and B. These are both square matrices. A is a 3 by 3 matrix and B is a 4 by 4 matrix. And I've put the main diagonal in green. Take these green entries and add them together to get the trace. For example, the trace of B is -1 plus 5 plus 7 plus 0 is 11. The trace of a matrix is a number. We'll be using transpose of trace later. My third and final topic for this week is the inverse of a matrix. Let's start by talking about numbers. In the real numbers, anytime we have a number A which is not 0, we have a multiplicative inverse called A to the power -1. So for example, if we have the number 4, then its multiplicative inverse is 4 to the power -1, or 1 divided by 4. And this is an inverse because it satisfies these two rules. 4 multiplied by 4 to the power -1, or 4 multiplied by a quarter, is 1. And a quarter multiplied by 4 is 1. I want to generalize this idea to square matrices, only to square matrices. Let capital A be a square matrix. If there exists a matrix B of the same size, which satisfies these two rules, AB is the identity matrix and BA is the identity matrix, then we say that A is invertible and B is called an inverse of A. If such a B does not exist, in other words, if A is not invertible, then we say that A is singular. Now, note that if B is an inverse of A, then that implies that AB is I and BA is I. But that's exactly the definition that A is the inverse of B. So if B is the inverse of A, then A is the inverse of B. We can say that A and B are inverses of each other. If A is invertible, then its inverse B is also invertible. Think about these two matrices. A is 2 minus 5, 1, 3, and B is 3, 5, 1, 2. If we multiply these together, AB, we get the identity matrix. I'll leave that for you to check. And BA is also the identity matrix. That means that A and B are invertible, and each is the inverse of the other. B is an inverse of A is an inverse of B. It's a fact that a square matrix with a row or column of zeros is always singular, is always not invertible. Why? Well, look at this example. Consider this A, this is a 3 by 3 matrix, and I have a column of zeros. Column 3 goes 0, 0, 0. I want to show that such a B does not exist. It's not possible to find an inverse of this matrix. So I'm going to start by multiplying the 3 by 3 matrix A, B, C, D, E, F, G, H, I by capital A. And I'm going to look to see what do I get. The first two columns I'm not interested in, so I've written these in grey. The third column goes 0, 0, 0. The third column is always going to be full of zeros. It's not possible to make this the identity matrix. It's not possible for this red entry could be a 1. It's not possible to choose A, B, C, D, E, F, G, H, I so as to make this red entry equal to 1. So it's not possible to choose a matrix capital B such that BA is the identity matrix. So A does not have an inverse. That means A is singular. Can an invertible matrix have more than one inverse? The answer is no. More precisely, if B and C are both inverses of A, then this implies that B is equal to C. Let's prove this. I'm going to start by supposing that B and C are both inverses of A. So I'm going to start by supposing that we know that AB is I is equal to BA, and AC is equal to I, which is equal to CA. But then look what we have. B, which is the same as B multiplied by the identity, is the same as B multiplied by AC, because AC is the identity. If we multiply three matrices together like this, it doesn't matter where we put the brackets. This is the same as BA multiplied by C. But what is BA? BA is just the identity. And of course, identity multiplied by C is just C. So now we can stop talking about an inverse and start talking about the inverse. The inverse of A is denoted by capital A to the power -1. So now our formula for an inverse is A multiplied by A inverse is equal to I is equal to A inverse A. Theorem: the matrix ABCD is invertible if and only if AD minus BC is not equal to 0. And in which case, as long as this number is not 0, its inverse is given by this formula. A inverse is 1 divided by this special number, AD minus BC, multiplied by, and look what we do. We take A and D and we swap their positions. And then the other two, the B and C, we put minus signs on. I'm not going to prove this now because we're going to generalize this idea to bigger square matrices later. This special number, this number AD minus BC, which tells us if a matrix is invertible or singular, is called the determinant of this 2x2 matrix. And we have two ways to write this, and we're going to be using both of these ways in this course. We could either use DET for determinant. The determinant of A is AD minus BC, or we could use these vertical lines. Vertical line, ABCD, vertical line means the determinant of the square matrix ABCD. So, for example, is the matrix 6, 1, 5, 2 invertible? And if the answer is yes, find its inverse. The formulae are at the top. First, we're going to calculate the determinant, and that will tell us if it's invertible or singular. If the determinant is not 0, then the matrix is invertible. If the determinant is equal to 0, then the matrix is singular. If the matrix is invertible, then we have our formula for the identity of A. So first, let's calculate the determinant. The determinant of B, DET of B, we multiply the entries on the main diagonal, 6 multiplied by 2, and then we do minus BC, or minus the product of the other two numbers. So 6 multiplied by 2 is 12, minus 5 gives us 7. Because 7 is not 0, we know that this matrix is invertible. And then we can use the formula in the yellow box at the top to write down the inverse of B. 1 divided by the determinant, so 1 divided by 7. 6 and the 2 swap places, and the 1 and the 5 get a minus sign in front of them. B inverse is 2 over 7 minus 1 over 7 minus 5 over 7, 6 over 7. Now I'm going to leave it for you to check that if we do B multiplied by B inverse, then we get the identity matrix. And the same if we do B inverse multiplied by B, I'll leave it for you to check, we also get the identity matrix. Let's do another one. Is this matrix invertible? And if the answer is yes, find its inverse. First, we calculate the determinant of this matrix. Determinant of C, minus 1 multiplied by minus 6, that's plus 6. Minus 2 multiplied by 3 is also 6. 6 minus 6 is 0. Because the determinant is 0, this matrix is not invertible. This matrix is singular. Inverse matrices can be used to solve linear systems. For example, solve 6x1 plus x2 is equal to 2, 5x1 plus 2x2 is equal to 3. Now, we could write this as vector equal to vector. 6x1 plus x2, 5x1 plus 2x2 is equal to the vector 2, 3. But the left-hand side is equal to a 2 by 2 matrix multiplied by a vector. It's 6, 1, 5, 2 multiplied by x1, x2 is equal to 2, 3. This matrix is just the one we looked at a couple of examples ago. It's the matrix I called B back then, and we found the inverse of this matrix. What I want to do is I want to take the bottom equation and I want to multiply both sides by B inverse. And to be precise, because these are matrices, I want to multiply on the left by B inverse. So I get B inverse multiplied by B multiplied by the vector x1, x2 is equal to B inverse multiplied by the vector 2, 3. But what is B inverse multiplied by B? That's just the identity. So on the left, we just have identity multiplied by x1, x2. In other words, on the left, we just have x1, x2. And on the right, we have a 2 by 2 matrix of numbers multiplied by a vector of numbers. We can calculate that. The solution to this linear system is x1 is equal to 1 over 7, x2 is equal to 8 over 7. In general, if we have a linear system like this, that's m equations and x variables, we can write it as a matrix equation. An m by n matrix multiplied by a vector, an n by 1 matrix is equal to a vector, and m by 1 vector, m by 1 matrix. Or as an even neater or shorter way of writing this, we could just write this linear system as capital A, bold X is equal to bold B. Now, clearly, if A is a square matrix and if A is invertible, then the solution to AX equal to B is X is equal to A inverse B. Just as we did before, multiply both sides on the left by A inverse. I get A inverse AX, but that's just IX, which is just equal to X. We'll talk more about this idea later. If A and B are invertible matrices of the same size, then AB is also invertible, and the inverse of AB is B inverse A inverse. So look what we do. When we take the inverse of A multiplied by B, we can take the inverse inside and put it on both of the matrices, but we also need to change the order of A and B. Let me prove this. I'm going to calculate AB multiplied by B inverse A inverse. And remember, when we can move the brackets wherever we want. So this is the same as A multiplied by B inverse A inverse. But B inverse is just the identity. So that's just A inverse, which is the identity. And for the other way around, we also have that B inverse A inverse multiplied by AB is equal to the identity. That proves that AB is invertible, and because inverses are unique, B inverse A inverse is the inverse of AB. Now, this is also true if we have more than two matrices. For example, the inverse of ABC, we need to change the order of ABC to CBA, and then we can put -1 on each one. C inverse, B inverse, A inverse. Or we could do this with 4 matrices, or 5 matrices, or 6 matrices, or however many we wanted. Let's just do an example to check this. Let's suppose that A is the matrix 1, 2, 1, 3, B is the matrix 3, 2, 2, 2. I'm going to leave all of these things for you to check. AB is 7, 6, 9, 8, and the inverse of AB is 4 minus 3 minus 9 over 2, 7 over 2. The inverse of A is 3 minus 2 minus 1, 1, and the inverse of B is 1 minus 1 minus 1, 3 over 2. Multiply those two together, B inverse, A inverse, and we get the same thing in green. 4 minus 3 minus 9 over 2, 7 over 2. Check my calculations here. Just as the theorem said, we should get the inverse of AB is B inverse A inverse. Next idea is the idea of powers of a matrix. Let's suppose A is a square matrix and K is a natural number, 1, 2, 3, 4, etc. We can define A to the power 0 is the identity, and we define A to the power K to be A multiplied by A, multiplied by A, multiplied by A, etc. So similar ideas as for numbers. Remember, for numbers, we might do 3 to the power 0 is equal to 1. For matrices, we don't have a 1 matrix, but we have an identity matrix. These are the same idea. If A is invertible, then we can also define that A to the power minus K is A inverse to the power of K. That means A inverse multiplied by A inverse multiplied by etc. multiplied by A inverse. And just like we'd have for numbers, we have the rules that a to the power r, a to the power s, plus s, and a to the power r, all to the power s, is a to the power r, s. Now, another theorem. Let's suppose A is an invertible matrix. Let's suppose n is a natural number or n is equal to 0. And k is some real number which is not 0. Rule number 1, if the inverse of A, then A inverse is invertible and the inverse of A inverse is A. We started off this chapter talking about how A and B were inverses of each other. A and A inverse are inverses of each other. A to the power n is invertible and A to the power n inverse is A to the power minus n. That's the same as A inverse to the power n. Ka is invertible and Ka inverse is K inverse A inverse. I'm going to prove part 3. Parts 1 and part 2 I'm going to leave for you. You should be able to write down a proof of part 1 and part 2. To prove part 3, I just do this. Note that Ka multiplied by K inverse A inverse. Because K is a number, we can move it about however we want. So this is just the same as, there's a typo here, this should be minus 1. K inverse K multiplied by A inverse. 1 multiplied by I is I. And similarly, K inverse A inverse multiplied by Ka, we can find is I. That proves that K inverse A inverse is the inverse of Ka, all inverse. You can do the same thing for 1 and 2. For example, if A is the matrix 1, 2, 1, 3, I leave it for you to check that A inverse is 3 minus 2 minus 1, 1. Then A to the power minus 3, that's A inverse multiplied by A inverse multiplied by A inverse. Check for me that we get 41 minus 30 minus 15, 11. Choose any two of these, doesn't matter which two, multiply them together. Whatever you get, multiply by the other matrix, and you should get this matrix in green. Moreover, A cubed, A to the power 3, which is A multiplied by A multiplied by A, is 11, 30, 15, 41. And the inverse of that matrix, using our formula, 1 divided by its determinant, 11 multiplied by 41, minus 30 multiplied by 15. You can check is actually 1. We swap the 11 and the 41, and we put a minus sign on the others. So we get exactly this green matrix, which was A inverse cubed. Check this calculation for me. If A and B are numbers, then we know that AB is equal to BA. So if we were doing A plus B all squared, we could use that property to change BA to AB, and we would end up with A squared plus 2AB plus B squared. But we can't do that for matrices because in general, AB is not the same as BA. So if we do this for matrices, the best we get is A squared plus AB plus BA plus B squared. Let's go back to talking about the transpose. That was the one where we flip rows to columns and columns to rows. Or I showed you a picture of a bit of paper. Hold the top left corner, hold the bottom right corner, and flip it over, keeping the top left as always the top left, and keeping the bottom right as always the bottom right. As long as the sizes are correct, and I don't want to talk about the details of that too much, A transpose is A. A plus B transpose is A transpose is B transpose. Ka transpose is Ka transpose. There's a fourth rule, which is perhaps a little bit less obvious, but it follows the same pattern as the inverse rule. The transpose of AB is B transpose A transpose. So just like we had inverse of AB is B inverse A inverse, we do the same thing for transpose. And the final point of today's lecture, if A is an invertible matrix, then A transpose is also invertible. And we have the formula that the inverse of A transpose is equal to the transpose of A inverse. And that's enough for this week. Next week, we're going to continue talking about invertible matrices. We'll start with an algorithm for finding A inverse. We'll talk about some more about invertible matrices. We'll look at a very big theorem called the invertible matrix theorem. We'll move to different topics of diagonal matrices, triangular matrices, and symmetric matrices. That's something that we'll need later in the course, so we'll get it out of the way now. And then we'll finish next week's lesson by talking about some applications of linear algebra. Are there any questions? Okay, so let me go back to the theorem. And in particular, I'm interested in number 2 of the theorem. The theorem says if A is an invertible matrix, then A to the power n is also invertible. And A to the power n inverse is the same as A inverse to the power n. I want to do an example which demonstrates this. So I want to take a matrix and then I want to show that if first we do to the power n and then we take the inverse, we get the same result as if we do the inverse first and then we do it to the power n. And I'm going to do this for 2 by 2 matrices. I've started with A, that's 1, 2, 1, 3. What is the determinant of this matrix? It's 1 multiplied by 3, which is 3, minus 2 multiplied by 1. The determinant is just equal to 1. A inverse is 1 divided by the determinant, so 1 divided by 1. We take 1 and 3 and we swap their positions. And for the other ones, the 2 and the 1, we put minus signs on them. That's how we find A inverse. Then I want to calculate A to the power minus 3, by which I mean A inverse multiplied by A inverse multiplied by A inverse. And I also want to calculate A to the power 3, and then I want to take its inverse. And that should be exactly the same according to the theorem. Now, I'm not doing the details here. I'm not showing this exact multiplication. I'm leaving that for you to do. Check that if we multiply these 3 matrices together, we do get this green matrix. Also check that if we do A to the power 3, A multiplied by A multiplied by A, we get this one. And then I want to find the inverse of A to the power 3. So I need its determinant. Determinant of A3, that's 11 multiplied by 41 minus 30 multiplied by 15. And if you have a calculator handy, you can check that is equal to 1. Using our formula for an inverse, the inverse of A cubed is 1 divided by the determinant. And then we take the 11 and the 41 and we swap their positions. We put a minus sign on the 30 and we put a minus sign on the 15. We get this green matrix, and just as the theorem said it should be, it's exactly the same as A to the power minus 3.